Okay, hi folks, welcome to the graphics programming virtual meetup. We follow the Berlin Code of Conduct. We have Discord server that you can join. We have a Twitter that we will announce our future meetings. And we have YouTube channel for all of our past meeting recordings. And here's an announcement. I'm not affiliated with GTC in any way, but GTC is a NVIDIA event for GPU computation. It has a lot of GPU stuff and even AI stuff, but it also have a bunch of graphic stuff that can be interesting. It is free and it is next week, so you can just register and join wherever you want. So today's topic is Wiki Mini Path Tracer Extra Chapter 7, where we finally start to use the Vulkan image. So far we are not using image. Instead, we just use a plain old buffer where we treat it as a 2D array and use it as image. That is because image is really complex subject in Vulkan. Or in any APIs, even in OpenGL, like having an image is just harder than other stuff. But in OpenGL, the driver already done a lot of stuff for us, like layout, map stuff like that. We don't need to worry too much about them. But in Vulkan, everything needs to be handled by ourselves, and that's why it's tremendously difficult to use image in Vulkan. So what is an image? First, the image can be 1D, 2D, and 3D. 1D is basically a line, and 2D image is usually what we use, but also there are 3D image, which can be useful for if we have 3D samples of something. Image can have different formats, like RGB is what we normally will have, but also we can have those kind of more performant compressed format that does not have significant visual quality reduction, and it can be faster on the GPU and smaller. Image can have different aspects, so color and also depth stencil. And Vulkan also have some other aspect flags, but I don't understand them. For color can represent a lot of different stuff from color, but also stuff like normal maps and like material attributes. They can all be considered color. But that's the aspect flag that we pass to Vulkan. Image can also have MIP maps. So an image itself is not a single thing, but instead we can have one large image and then we just reduce the size by 2 each time to have smaller images, and then sometimes we can sample from the smaller images. MIPMAP is useful to avoid aliasing. For example, if we don't have any kind of MIPMAP, and then we use the nearest point, then we get this horrible artifact. But if we apply some MIPMAP and use more advanced filtering, then we get smooth image. And the image can also be an array with multiple layers, because just consider, for example, in PBR rendering, you probably will you probably need to have multiple layers, like normal map and stuff, and then they compose into one image. And also, for each layer, they will have a MIP map, but the MIP level of all the layers need to be the same. And the MIP of a layer is called a sub-resource. So it's like a layer contains a bunch of sub-resources, and then the image contains an array of layers. Image can also be multi-sampled, like each texel can contain information of multiple samples. If we want to do some stuff like MSA, then this can be really useful. Image can have different tiling. So there are two kinds of tilings we need to care about. One is optimal, which is implementation dependent, as fast as possible tiling. And the other one is linear, which is basically row major arrays. And the linear tiling is useful when we want to read the image on the CPU side, because otherwise we have no idea how the underlying data is stored. Image can have usage flags. This is the same as buffer. We can say it can be used in compute shader, it can be used in vertex shader, etc., etc. Image can also have different layouts. It can be usually initially it's layout undefined, and then we can transit this layout into like layout general, layout transfer, source, optimal, stuff like that. And certain Vulkan operations can only be used when image is under certain layout. So this can get really complicated. Also, there are image view, which is range of sub-resources of image used in different format than they were created with. So we can do stuff like cube mapping, and can like remap the different channels of the image. And the other object we can't have is a sampler, which if we want to use texture sampling, we need a sampler. Since this tutorial, we just write to all the image in texel by texel basis. We can ignore the sampler. And the outline of using image instead of the current buffer approach is, first, we need to have two images. One is a device only one, and the other image is accessible from both the CPU and GPU. We don't need any MIP map, and we don't need an array. And both of them will use RGBA format, because GPU are not optimized to deal with 3-component stuff. Instead, it's always like 16 bits, 32 bits, etc., etc. So the first image will have tiling optimal, because that would be faster, and it's initially it's layout undefined, and it is divided local memory. The second image needs to be linear tiling, because we need to read them from the CPU side. It also started with the undefined layout, and And it need to be have all those memory flag for host visible, host coherent, blah blah blah, to make so we can read them from the host. The image view will point to the first image, since we only ever write to the first image in the shader, and then we just copy the result into the second image so we can read them from the CPU. And then we need to have a transition of the image layout of the first image from the undefined into the general layout, and the second image from the undefined into transfer destination optimal. And with this kind of transition, with the image memory barrier, so after rendering the image, we need to transit the first image's layout again from the image layout general into image layout transfer source optimal, because then with after that, only after that we can copy it to the second image. Afterwards, just like in the buffer example, we need a pipeline area to say, hey, this memory is ready to read. And our first code change is we need to remove the width and height from the push constant struct, since we can read them directly from the image now in the shader. So we don't need to push constant width and height. So we can just remove them, and but in the C++ side, we still need to define the width and height. We just don't need to put them in the push constant. Then it's creating images and the image view. Then we have this code to create our buffer. We can just delete that, and to have this code to create an image. And consider image can have so many different properties. This code gets rather daunting, but basically, physically, it's the same thing we talked before. We have a 2D image. The format is RGBA float. We have extent where it's width and height, and the third dimension, because we have 2D image, is just one. We have one MIP level, one array layers. We don't have multi-sampling. We want tiling is optimal. Usage, we both use as storage buffer and then as a transfer source, and then we don't share the image with different queues. The initial layout is undefined, then we create the image. Then we create the image view. In the image view, we need to specify what image we refer to, the view type, which and the format. Then we need to specify which kind of sub-resources we need to refer to in the image view. In this case, we only have one layer and one MIP, so it is easy job. And then we have image view. Then we have our last linear image that we use to read from the CPU. And it is I just changed the tiling to read, tiling to linear, sorry. And also the usage, we need to transfer destination, since since we copy the image into this image linear. And then also we need all those memory flags to make to make it possible for the host to read the image. Then there is the annoying part of this is the layout transition. For the layout transition, we need image memory barriers, as I said before. And for image memory barriers, it is a lot like the global memory barriers before, but that they can represent execution dependencies and memory dependencies. But they can also have transitions, the layout of image, or the transfer ownership of image between different queues. And also they can have only apply this to a range of sub-resources. So they don't need to apply to the whole image. And we need the two image memory barriers. One to make the image accessible for shader read and write. Also need to transfer from the undefined layout into the layout general. For this image linear, we need to make it accessible for transfer write and also make the image layout transfer from undefined to the destination optimal. So we already have this code here. Dot, 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 currently I put the dot, dot, dot here. Currently it's nothing. And we have this particular code that we just create two buffers. And using the upload command buffer. Since we already have this command buffer, we can just also put the image layout transition into this buffer, this particular buffer. So before the dot 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 part, we can put this code here, where we first say the source was not accessible, so the source access flag is 0. But the test image need to be read and write from the shader, and image linear need to be write from the transfer. And also NVVK have this make access mask pipeline stage flags helper to figure out how to create the pipeline stage flags. Afterwards, we can just create all those image barriers that use access flag we defined before with corresponding images, and also have corresponding transition from undefined to general and from undefined to transfer destination optimal. And then we can have this command pipeline barrier where we just specify those two image barriers. And then we need to modify the descriptor set a little bit. So instead of using buffer, we need to use an image. So the descriptor type from storage buffer becomes storage image. And also we change the name of those constants. This constant to reflect that we have image now. So and for write descriptors and sets, we need to make similar changes. Especially we need to see the image layout general, and the image view is the image view we have. And then we also need to modify the dispatch, because our push constant, we cannot use a push constant struct to get the width and height. So instead we just get width height constant directly. Then the next part is copying image. But before copying image, we need the image image memory barrier again. So So we need this memory barrier where the source is treated right, and then we need to transist the image into the host read. And then, oh, sorry, this is the old code. This is old code for making the just buffer ready to be read on the CPU side. We can just delete this code and oh, that's a mistake. So I didn't include this particular code. But the idea is first we need to transist the image into the layout transfer source, and then we need to just do the image transfer, and afterwards we need to have a barrier like this, but instead this barrier need to transist on the, well, not transition, just to state that the image is ready. And then it's just mapping the buffer. In this case, it's become mapping the image. So we had this particular code before, where we call this MVVK allocated map. And for some reason, MVVK allocator doesn't support mapping image. So we need to do this. We need to do this instead. We just use VK map memory and the VKL map memory directly instead of using MVVK's helper. And otherwise, it's the same. Also, we need some kind of cleanup for the image view and the image we created. Now in the GLSL side, it's the same thing. Since we modified the descriptor set, similarly we need to change our binding here. Just our variable here to what to image 2D, and specify the format as RGBA and this 32-bit float. We also need to get the image size directly from the image instead of from the push constant. Also, this image size returns IVEC2 instead of UVEC2, which means when we use resolution.y now, we get a signed integer. That's why when we use them in the random number generator, we need to cast the signed integer into unsigned. GLSL also have those two built-in functions to load and store images at a per pixel basis. Those two functions has a lot of overload for different image types, like 2D, 3D, 1D. But since we are using a 2D image, those two signatures are the ones we want. And we can use image load and image store in our code by replacing this buffer reading and write with this particular code, where everything is still the same, almost, but for the previous average colors, instead of reading from the buffer with the array syntax, we use image load. And at the end, instead of writing to the buffer with the array assignment syntax, we have this image store. And yeah, that's it. Any questions before I end the recording? Okay, I will end the recording. Oh, there are some chat. What a weird texture. Crazy how verbose it is, even when using MVVK. MVVK really don't help anything with images, it seems. It doesn't help anything. It's probably helps something with allocators, but I don't think it help anything with images. It's basically raw Vulkan in this code. I will stop recording now. Oh, there's another chat. I'm on AMD, and if I were using Vulkan, I'd try to avoid the NVIDIA libraries. I don't think that matters.
Yeah, they shouldn't change whether you can use. Having an AMD card should not infringe your ability to use the NVVK helper libraries at all.
Yeah.
Yeah, that's kind of, sorry if I didn't want to interrupt, so I thought I would use the text. So does this NVVK library actually work if you're using an AMD GPU?
Yes.
Yeah.
Oh, okay. That's
But
kind of surprising.
I never used it myself on AMD GPU. I only use it for this retracer project. But I assume it will work if it is well written enough.
Is it basically just like a wrapper library that like just makes things easier?
Yes.
Okay. I guess I should try and download it and build it and see what happens.
So it's a part of the NVIDIA samples repository. And if you're wanting to use the NVIDIA specific extensions, the ones that end with NV, then you will have to have an NVIDIA card because that's the only cards that are going to support those extensions. But things like the VK Mini Path Tracer, the KHR ray tracing is cross-platform, and it should work because there's nothing specific to NVIDIA when you're using the cross-platform extensions or not using extensions at all, or any of the other basic stuff that the NVVK helpers help with.
I'll give it a crack then. Thank you. I'm just used to like the NVIDIA stuff, like with CUDA versus OpenCL and so on. So.
Yeah, it's not like that, thankfully.
Okay, cool. Yeah, thanks. I'll check it out.
Oh, that's good to know.